So this report is titled Atmospheric Carbon Dioxide Removal, a Physical Science Perspective. So it looks at all the standard CO2 drawdown methods and put some physical science behind them in terms of limitations, costs, pros and cons, and then make some recommendations for how such research should be funded, or what are the basic science questions that have to be asked before funding any research in these techniques and implementations, testing, monitoring, reporting, validation, verification, etc. So we'll read, it will be a few podcasts depending on how much I read. It's a long report, it's a nice report. I'm cutting it short, especially the technical appendices which provide all the reactions and calculations and so on. Let's start with the executive summary and see how it goes. Humanity's activities currently lead to a net increase in atmospheric carbon dioxide by more than 15 billion metric tons per year. We already know this. We have looked at it many times. Concerns about the global consequences of this continue to rise, are continuing, so there's an R missing, coupled with growing global energy needs, political constraints, and economic challenges that limit the rate of reduction of global CO2 emissions, and they are driving strong interest from both the public and private sectors in the development of atmospheric carbon dioxide removal methods. CDR implementation, carbon dioxide removal is CDR. CDR implementation methods, sometimes referred to as negative emission technologies, reduce the CO2 levels in the Earth's atmosphere by removing carbon dioxide molecules from the air and sequestering them for a very long times. These approaches are distinct from carbon capture and storage technologies that remove CO2 at fossil fuel powered sources such as the power plants or cement production facilities. CCS at fossil CO2 point sources can help reduce emissions but does not remove CO2 that is already been thrown into the atmosphere. Residence time is multiple centuries, so we have to take it out. This report provides an overview of CDR. It's also referred to as DAC, direct air capture, and their fundamental physical constraints is what is the focus here. We focus on CDR approaches that have the potential to contribute to CO2 removal at the gigaton per year scale, where 1 gigaton is 1 billion metric tons. And remember, this is the potential to contribute at gigaton scale. This is the scale of effort that would be needed to have a meaningful global impact. For those making and implementing policy, the general findings and recommendations of the report may provide a helpful science-based perspective for those supporting or working directly on research and development efforts, and for those with some scientific background interested in a deeper understanding of the issue. The main text of the report includes concise but relatively self-contained descriptions of various technical and scientific points relevant to the broader conclusions of the report. The central findings and recommendations are outlined here. We will look at Section 7 in the end provides more detailed guidance for policymaking and for potential funders of CDR research, pilot programs and technology that we will read through. Okay, what are the main findings? CDR approaches divide loosely into two distinct categories: cyclic and once through. So it's like a circular economy type. You capture, you use it, release it, and capture it back, so you keep it in a loop. Or once through, so air flows through, you capture it and then you put it away somewhere. CDR methods in these two categories have different features and challenges. Many approaches have been proposed in each category, although most approaches are still at early stages of development. So cyclic CDR systems such as chemical direct air capture use the same material to capture atmospheric CO2 over and over. So you have adsorption and desorption. These systems are necessarily energy intensive, but may enable carbon sequestration that is easier to verify and has less environmental impact than other approaches to CDR. Once through CDR systems, on the other hand, are enhanced rock weathering, involves the single use of a resource. So you chop up, grind up rocks and you spread them, and because of the small sizes and large surface area to volume ratio, the weathering rate can be enhanced to take down CO2, because weathering is a natural process via which CO2 is drawn down. For example, many such approaches employ minerals extracted from the earth to directly or indirectly absorb CO2. These systems may use less energy, but they generally require extensive resource extraction and may have significant environmental impact. Their effectiveness has been challenging to measure and verify. So if you just throw ground up rock somewhere on the, let's say, farm, and enhanced weathering is happening, but how much additional CO2 is being really taken down? That's not very easy to measure. The second finding, CDR at the scale of many gigatons of CO2 per year requires large amounts of energy, particularly for cyclic processes where you are absorbing, absorbing, and so on. Those processes are energy intensive. Okay, so there are some numbers there in terms of energy consumption. So the laws of physics, for example, dictate the absolute minimum energy needed, which is comparable to the combined electric consumption of 11 million average US households in 2021. So that's 14 gigawatt years energy unit. So the cyclic CDR approaches currently in development include existing small-scale installations require at least several times the theoretical minimum energy requirement for any amount of carbon captured. Okay. The third finding says CDR at the scale of many gigatons of CO2 per year requires processing large quantities of materials, particularly for once-through processes like enhanced rock weathering. Finding 4, unlike past experience with computing technology, there is no prospect of exponential growth in capability for any CDR approach. So based on these findings, the report recommends that research and development on CDR be selectively and prudently pursued despite many challenges described in this report. Essentially, it's now guaranteed that we will need carbon capture from the air as a part of the portfolio that will get us to stay under 2 degrees C, or 1.5 degrees C is pretty much gone, I suspect, but also just generally to keep the warming as low as possible by 2100. Recommendation 2, the prospect of large-scale CDR should not compromise efforts to reduce carbon emissions. So that's kind of a moral hazard that's already always hanging on our head, in the sense if we start becoming very good at CDR, will people then just say, or industries just lobby for saying, anyway, we are drawing it down, so why not just continue to burn fossil fuel? But there is a hysteresis effect. For example, if you put CO2 out and capture it, in the meantime there may be ocean acidification happening, many other harmful impacts on ecosystems and so on may happen if you just don't eliminate fossil fuels and the emissions instead of emitting and then capturing. Okay, so that has to be very carefully looked at. Recommendation 3, ecosystem-based CDR approaches should be pursued when they are feasible and effective, and do not compromise food production or other priorities. So bioenergy, carbon capture, sequestration, BECCS, and other biological approaches tend to rely on growing feedstock for bioenergy, where the land and the water could be competing with food production. So who benefits from bioenergy and who pays the price has to be very carefully tracked. Okay. Recommendation 4 then, CDR planning must incorporate substantial additional carbon-free power sources, particularly for cyclic processes. Such planning should also consider the land or sea area required, and impacted. So obviously, if you are doing adsorption and then heating material up for desorption to reuse the material that will precipitate out CO2, then you need a lot of energy. That energy better be renewable energy, so that you are not trying to get fancy about capturing CO2 and then using fossil fuels or carbon-based energy that doesn't give you effective additional carbon sequestration. Once through CDR approaches should be or should not be deployed on large scale until research determines their effectiveness and impact. So enhanced weathering, enhanced rock weathering already is being debated about what it will do to the soil, whether it will increase methane emissions and so on and so forth. So once-through approaches generally are hard to monitor and verify, but also they can have other impacts. So you need research and small-scale trial projects before any attempt at large-scale implementation of these approaches are deployed. Okay. Recommendation 6, reliable systems of measurement, reporting and verification MRV must be developed for CDR systems. Robust standards for sequestration and for safety and environmental impacts are also needed. So we have been increasing CO2. If we start drawing down, will the system just go back to normal? And will there be a shift of rainfall, temperature patterns, extremes and so on? We don't know the return path is going to be smooth or not. Plus, if people are going to start using carbon capture, carbon dioxide removal as part of their offset, then you have to be sure that actually there is additional CO2 being removed by CDR systems, so that MRV or monitoring, reporting and verification becomes a very integral and critical part of the system. Economic and policy frameworks for carbon management should be designed and implemented. Such frameworks are needed to facilitate balancing the costs and benefits of large-scale CDR and emission reduction strategies, obviously, right? So nothing will work unless they are economically viable, and policy frameworks must incentivize behaviors which favor carbon management in a sustainable fashion, but also avoid the moral hazards of continuing to emit because we are doing CDR. So the report basically focuses specifically on some of the fundamental physical limitations of CDR methods and how these limitations constrain existing and proposed CDR systems. I'm going to be brief about it because each chapter has a summary, and I'll just read the summary and some additional points very briefly. The report considers a broad range of approaches to capturing atmospheric carbon in the form of CO2. Methane and other non-CO2 greenhouse gases are discussed briefly in one of the appendices. This report does not cover technologies for carbon capture at fossil fuel-based point sources, so at the drilling sites and so on. Solar radiation management efforts that would, for example, reflect some solar radiation without addressing the underlying atmospheric carbon issues are also outside the scope of the report here. This report summarizes the basic physical limits and scaling aspects of several approaches to removing atmospheric carbon. It does not attempt a detailed comparison of specific technologies, nor recommend specific companies or enterprises in this domain, so it's more focused on science and advice for governments and funders. Understanding the principles underlying the wide range of proposed CDR methodologies and the constraints on these approaches involves concepts and analysis from many fields, including physics, chemistry, biology, and earth sciences. To make the report as readable and self-contained as possible, we include a number of technical appendices with concise descriptions of some key scientific principles relevant for the systems described here, as well as a glossary of terms and acronyms. In various places, we have included back-of-the-envelope estimates that are intended to communicate the scales involved or plausibility of certain issues or assertions. These estimates are not intended to provide precise estimates or values. Okay, so it's useful. Make some additional points that, in addition to what we have been reading already. So maybe I should come back and continue this in the next podcast. How long am I here? It's about 14 minutes, so that's a good point to stop. And it's getting very warm. I forgot to turn on the fan. So we'll come back and look at anthropogenic CO2 and motivation for CDR, which we already have, but we'll briefly read a few points, and then we start moving to specific approaches of technical and once-through CDR systems, and then some details on the physical principles, limitations, pros and cons and so on. Okay, so see you in the next podcast on this topic.